about equilibria. Equilibria. And I know it's typed up there, but I'm going to nicely handwrite it. Oh, is my pen down? That would be irritating. No. Oh no. Might be whiteboarding this one. That'd be fun.
Why?
You know what? I know I'm not set up for it. And every time I try, it makes me angry at life, the universe, and all of it. So equilibria is related to reaction kinetics. All right, and when I say reaction kinetics, I'm talking about the stuff we just did, where we talked about the rates of reactions. So I want to imagine this. Imagine the decomposition of water. I'd like you to write me. I'd like you to write me a balanced chemical equation for that. The decomposition of water. I better remember to go buy new batteries this weekend, or I'm going to have an annoying Monday. I have to make sure I go buy new batteries. Otherwise, there's no way this will hang on until Monday. And I'll come here Monday and be like, oh, I can't believe it's dead. And you'll be like, but didn't you know that Friday? And I'll be like, quiet. So I just want to skip all that by getting batteries. That's unlikely. Okay, come on, decomposition of water. Balanced. I want everyone to answer it.
Did we start off with liquefying H2O or gas?
Yeah, whatever. For the purpose of this, you could do it either way. But if you're doing it by hydrolysis, which you've done, that would be liquid. Okay, water, of course, is H2O. And when we decompose something, what are we doing to it? Breaking it apart. So let's assume this is a liquid. What's it going to break apart into? Well, there's only one thing it could break apart into. Yeah, we could get hydrogen, and we could get oxygen. Of course, the most common form of hydrogen is, diatomic hydrogen gas, right? Comes in pairs. One of our diatomic gases, right? Hofbrinkel. And oxygen is also one of our diatomic gases. And what do we note here? Yeah, I've got two oxygens over here. I've only got one over there. So the law of conservation of mass says I got to do what? Yeah, so I got to stick a 2 up there, right? And what does that do? Yeah, so it fixed my oxygen problem, but it gave me a hydrogen problem. So there we go. It's true, basically. How's that? Does that make sense? That feels comfortable? Okay. Now, what I want to talk about today is the rate of this reaction. If I were doing this reaction, that's quite delicate and fine, but maybe a bit more delicate and fine than I want. If I were finding the rate of this reaction, what would it be? What would the rate law be? Yeah, some constant, and we just use letter K. By the way, there's something magical about the letter K. Yeah, it's from the German constant. In German, constant starts with a K, so we use K. That's it. That's all. It's like when you see people driving the Mercedes, and it very pretentiously on the back says compressor, but spelt with a K. And they're like, that car must be expensive because they spell compressor with a K. But for some reason, that same rule doesn't apply when you're like, oh, Quickie Mart with a K, eh? And I don't know. I don't know what the difference is. But anyway, so the rate is equal to K, and then what? Concentration of H2. And there'd be some exponent there, right? Now, do we know what that would be? No. And then what? Cool. Do we like that? Is that true? I wrote it because you told me to write it. Does how fast a reaction happens depend on the products? What does it depend on? Okay. And the reactants. Because what's making it react? Yeah, no worries. No worries. You fooled me too if it's any combination. I just blindly wrote down what you told me to write. But then I started getting a sense of like, wait a minute. And then I thought I could probably make it like I knew this was the wrong thing and I was being coy. Then I dropped the ball. So now we'll just be honest. I didn't know. But here we go. So it's going to be the result of how much water I have. This is logical, right? When there's lots of water, it's easy for water to bounce into each other and cause that break apart, right? When there's no water left, what will the rate of this thing be? Yeah, obviously none. Right? Does that make sense? Okay, perfect. And how would I figure out that exponent m? Here's our test round. Before I mark, you did very well on this question. How would I figure out what that exponent is? With the things and the stuff, and I'd have to do all those things and to the stuff. And I'd probably want to look for other things. Numbers, going to use numbers, going to be some numbers, and maybe to do the stuff to the things with the numbers.
That's pretty much all I did.
That's right. Yeah, I mean, that's all life is. It's just things and stuff with some numbers every once in a while. And tears. There's going to be tears. And smiles. There'll be tears and smiles. So we would have to actually do an experiment with this, right? We would have to set up a reaction, and then we would have to change the concentration of water. Now, interestingly, this is one where the concentration of water isn't going to change very much because, most times when you have a big old bucket of water, but we could change the amount of water. We could do this with water vapor and things like that. So this is great. We could determine M, and once we had determined M, we could go back and determine K, right? Relatively easy thing to do. Quiet. Here's the problem. What about, let's do a different reaction. Let's do the combustion of hydrogen. Write that reaction out for me, and write a rate law below it, please. I want you to do the combustion of hydrogen gas, and below it, write a rate law. Ooh, and while you do that, I'm going to do my attendance from yesterday.
Are you just going to do yesterday's and then just stop and like not do
I actually have yesterday's done for once. So today I'm joking. Today I'm going to do just today's. Holy crap. What time is that grad support session happening?
9:30.
And then is it all day?
Yeah.
Okay, because like my entire grade 12 math class is signed out. And no, listen, and if that's legit, like
It is.
primo. I will prep. Oh, I will be so mad at that kid. And it'll be one of the ones who never shows up any other day too. And it'll be like, curse you. Because if it's actually that's right. Because if it's legit empty, I will get so much work done.
This shop has me as an only grade 12 student at the same time.
This is actually awkward because you're all marked absent right now too.
Does that mean with that?
So why did I?
No, it doesn't. It just means I don't know how to indicate who's actually absent. I guess that makes it not my problem. I'm just going to say complete.
For tomorrow.
All right, submitted. Huzzah! I'm going to double check yesterday and make sure I'm not lying when I say it's done. Hey, it was done. All right. I'm so good. Quiet. Quiet. All right, do we have this reaction yet? Do we have the rate law yet? Okay, who can tell me what the reaction is? Sorry? Ah, so what is that? All right, so there would be our reaction. And what would the rate law for this be? Yes, Ms. Pelchier.
What is the form of H2O made from the combustion reaction made naturally?
Let's say I put some ice cubes in the room. That water will condense. Is it 2? Cool. Yeah, like here's the deal. The water may be a gas initially, but if I turn it into a liquid, then the end result would be this. Does that make sense? Every reaction has middle steps that we're not seeing. So this is a possible reaction. This is also a possible reaction. Does that make sense? In this case, I'd like to do this one.
Why do we never use solid?
If you'd really like. I mean, we do all the time. Like I put in my drinks just about every day. No, and I'm not saying that to be coy. Do you know when I got my first fridge that had like an ice maker in it, it was like one of the happiest days of my life.
I've never had one.
I got my first one last year. I bought it used on Kijiji for like $300. And then like I had to like install all the plumbing myself and get all set up. And then like that first time I put the cup up and it was like ka-chink, 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 ice cubes. I was like, where have you been the last 34 years, ice cubes? And so yeah, it was an exciting day for me. And yet it totally is. Like that didn't faze me one bit. Which is weird because I think my first like couple weeks here it did faze me. And then yeah, not at all. It just which is why, I mean, this has nothing to do with chemistry. It's horrible if something bad actually happens. Like we hear screams. No, but you can. All the time. I think you can tell the difference.
There's a difference between like just want to stop screaming. And
yeah.
You heard that a couple weeks ago. It sounded like someone was actually getting murdered up there.
Well, hopefully nobody was. But no, but I think like the fact that that could have just been me. Was it second period? And because I'll tell you, I have some days when I just go in the hall and go like, and then like go back into class. Last year, I won't say his name, but I had a student who had some anger management issues in one of my classes, and it was really funny because I was working with this kid really hard to try and keep him from getting suspended because he had a lot of suspensions, and that's not helpful, right? Never understood this thing of suspension as punishment. It's like, hey, you who has trouble behaving well in school,
go home.
Stay home. That'll fix you. Like I've never understood it. As I get when it's a safety concern or something like that, but you know what I mean? If it's just, well, that's my problem. It kind of seems to me like a reward. So anyway, so this kid, he was a nice kid, but he would just blow up. And so we had a system where I'd be like, listen, I'm not saying don't blow up. I'm saying go outside. And so he'd be in class and all of a sudden he'd look at me and go like, I'd go, yep. And he'd go out in the field and like, and you'd hear the language that could like strip the paint off a barn and then like just come back in and sit back down and keep doing his fractions. And we had a system. Anyway.
It doesn't really like.
If you're wondering, by the way, that's how they used to strip the paint off barns. You know, before the invention of the pressure washer, they'd just go out and just let loose. It just falls right off. Anyway. In all seriousness, though, I think it speaks to why communities that integrate students with special needs is such an important thing. Because instead of things seeming strange and bizarre and other, it takes very little time to just discover that these are part of the normal human experience, and that's a valuable thing. Anyway, soapbox stepped down from. What is the rate law for this second reaction, for the combustion of hydrogen gas? Is it? Does the rate of this depend on some constant K times the concentration of H2O to some exponent M?
No.
No, why not? Yeah, because the rate of a reaction doesn't depend on the products. It depends on the reactants. So this would be the concentration of H2 to some exponent. Doesn't matter. I've used M already. I'm going to use Q. Try and stop me. And then what else? Yeah, it also depends on the concentration of oxygen. And I'm going to use R. And again, I invite you to prevent me from doing so.
What if we just all fought you right now?
I'd win? What kind of question is that? Have you seen me lately? I'm very tough. It's one of the first things people notice about me. So,
Oh, very nicely. Mr. Lindell challenged chemistry and math.
Oh, he did.
to what?
He said that
To a boring off, he wins. Oh, take that, English. Yeah, this is recording. You can all show it to him. Chemistry will take on English any day.
He said science and math are useless.
English? Who speaks English?
Only.
I have never used English, but parabolas every day. Every day. I meet people on the street and I'm like, vertex form. He's like, am I right? But we don't say it in English because who speaks English?
You say it in like the code
Fair
number.
point.
We just
1, 2, 4.
I just pull out my whiteboard, you know, the ones with like the grids already on it, and I just plot some points. And he's like, I get you.
But like to say that he plots points.
Exactly, yeah. English.
1, 2,
God.
0.
This is on the phone is just a bunch of random numbers that you say to speak to one another.
Yes. You know, when Carl Sagan, the famous gold record that they sent up with the Voyager probe, what did it have on it? To introduce us to alien species so that they would know about us. It's actually, have you ever read about that? Did your grade 9 science teacher have you read about that? Because if they didn't, I encourage you to go home and read all about it. It's super fascinating, super interesting, because it's such a, like, this is such a grade 9 assignment, right? Like, if you had to make a record of human history and you could fit, like, you know, 200 megabytes worth of material, what would you put on it to introduce us to an alien species? And it's such a thing where, like, whatever, but when you actually stop and think about it, like, it's one thing when you give that as like an assignment to grade 9s. Now imagine it's like, hey, we're spending billions of dollars to send a probe outside of our solar system. We're actually going to do this. What do you put on there? Fascinating, right? So we put people saying hello in every single language that we knew about on Earth at the time. Pretty cool. We put the mathematical proof for pi, right? Like how pi is developed, and the Pythagorean theorem. Because to the best of our understanding, those are universal things. We put music. You know, so it's an interesting thing. Anyway.
That's a bad idea. You could kill a whole race. Did you not see that when Mars attacks?
I did see When Mars Attacks. I like When Mars Attacks.
This is why we can't find aliens. We keep murdering them all.
With my music. Like, damn you, free jazz. You killed another species. All right. So here we have two reactions. And the problem is, these reactions are the opposite of one another. Are both of these possible reactions? Are these both reactions that happen? Yeah. So we have a situation wherein we have two reactions that both are real, that both happen. And if I want to take it from this specific for a moment, maybe we could generalize a bit. And I could say I have one reaction where A becomes B. Doesn't matter what it is. And I have a second reaction where B becomes A. Imagine that you went to your work and you did a job.
That's great.
And maybe you're putting something together. You're doing assembly. Maybe you're like on a factory line and your job is to put bolt 137 into, you know, its appropriate slot and connect two pieces of metal. And that's what you do all day, right? You just do one thing. A turns into B. Next one on the conveyor belt. A turns into B. Next one. A turns into B. Okay, that's like a chemical reaction, right? You're taking consistently one reactant, whatever it may be, and turning it into a product. Can you picture that? What would happen if the next guy on the assembly line's job was to do the exact friggin' opposite. Take the bolt out, take the bolt out, take the bolt out, disassemble. That's what this is. When you have two reactions that are the opposite of one another, one reaction is building something, the other action is taking it apart. Those two reactions, in theory, do what? They cancel each other out. Does that make sense? Now, in this case, if this is true, then we could say this. The rate of the first reaction would just be, I'm going to call it K1 times the concentration of A. Right? The more A we have, the faster this reaction will go. Right? The second reaction will have some different constant K2, and it depends on the concentration of B. And I'm not even going to worry about the exponents for right now, though I guess we could. I could put an M there and an N there. But let me ask you this. Let's imagine we start with only A. We start with only A, we have no B. What's going to happen? Well, which reaction is going to happen? The first one's going to happen, right? Will the second one happen right at the beginning? Why not? I don't have B. Why does that matter? Yeah, that's what it starts with. And the rate of that reaction is a constant multiplied by how much B I have. Well, if I have no B, I have no rate. So when we start with only A. And that means reaction 1 goes as fast as it's ever going to go, right? 2, not at all. Okay. Except as reaction 1 goes, what happens? Well, B gets made, right? What else happens? We are making B. What else are we doing? We're losing A. Does that make sense? What is that going to do to the rates of these reactions? Reaction 1 will start to... Reaction 1 slows down. What about reaction 2? Yeah, reaction 2 starts. But it's going to start really fast or start really slow? Which one? It's going to start slow. Now that means that B is being made kind of at a medium pace. Right? And A is getting lost at a medium pace. But then B is also being used slowly. And A is getting made slowly at the same time. Do you start to see where this is headed? What's going to happen eventually? What do you think? Will we ever use up all the A? No, because as we use A, we make B. But as we make B, what's going to happen to the second reaction? It's going to speed up, and it's going to make A. And eventually, what's going to happen? What has to happen? Eventually, something will happen. So as time passes, we can say this. Rate 1 is going to get slower and slower. rate 2 will get faster and faster. And remember, rate 1 is starting at the highest speed it can reach, right? Rate 1 is never as fast as right off the hop when there's all A and no B. Does that make sense? Eventually, these are going to hit a magical place where what becomes true? Yeah. Eventually, if one thing is slowing down from a top speed and the other is speeding up from no speed, at some point, rate 1 will be the same as rate 2. And if we go back to our factory analogy, it means this. At some point, I will be disassembling B as fast as the person before me was assembling it. And when that happens, well, then what happens? My battery runs low. Is that a metaphor? I don't know. Eventually, when this happens, let's say what we're building in the factory is cars. And let's say early in the hop, we have all the supplies to make them. So we're making lots and lots of cars, right? But then who would I put in charge of the unmaking work everyone has done? It's Caleb. So Caleb leads his crew. And at first,
Why am I taking part first?
just for the sheer joy of deconstructing somebody else's work. Are you on board?
How much should I get paid?
Well,
Okay, then, yeah.
better than Team A.
Okay, good.
All right, good. So there we go. So Caleb's on board. So now, at first, he's got to look all over the parking lot to find the couple of cars that have been built. His job's pretty hard. He's got to hunt them down, big distances between them. But the construction guys have got it easy. Tons of parts, materials, everything. They're making cars really quickly. Caleb's taking them apart pretty slowly. But slowly, it gets harder to find parts in the factory. The rate at which they're building cars gets a little slower and slower. At the same time, Caleb's team, lots of cars right now. We're hitting our stride. We're getting quick. We're taking them apart. And at a certain point, we've got a bunch of cars made. We've got a bunch of parts left, right? It's not that all the made cars disappear. It's not that all the unmade parts disappear. But at a certain point, Blaze's construction crew, building them, the assembly team, is building at the exact same rate Caleb's team is disassembling. To all the world, what does it look like? Like it's pointless. In other words, to all the world, it looks like what's happening? Nothing. If I've ordered a car, is this factory working overtime helping me? No, they're not actually producing anything. Production stops. Now, it's a great analogy because in that analogy, have the people stopped working? The two reactions are happening all the time. Blaze's team building cars like crazy. Caleb's team, mirthful with a smirk on his face, taking them apart, making eye contact the whole time. All right? But they might as well not be running at all. There might as well be no factory. Might as well close your doors because when the rate of production equals the rate of destruction, we enter a steady state where the cars that are made, the cars that have already been made and are off in the lot, they're there. The parts that are present are still there, but any parts that get turned into a car are matched exactly by a car being turned into parts. And the net result is that there's always the same number of completed cars, and there's always the same number of incomplete cars. Does that make sense? At a certain point, rate 1 equals rate 2, and this is a steady state. And we call this steady state chemical equilibrium. Have you guys heard the term equilibrium before? So equilibrium is a state of balance. It's a state of maintenance and balance. Your body has biological equilibrium. You probably learned about it in biology class, right? where your muscles produce heat just by moving around. Your blood moves that heat throughout your body, but then that heat gets bled off the atmosphere. And your body temperature is constant because you're in a state of equilibrium. Your body will use its muscles, even for nothing, even if you don't otherwise need to make sure that you stay warm enough to match the heat that is lost to the atmosphere. And your heart will, your vasoconstriction or dilation will take place so that if one part of your body is getting cold, the body sends more blood there to if you have lower blood pressure, which many women tend to have lower blood pressure, your body has trouble reaching steady state equilibrium at your extremities. So we often hear women complain that their feet are always cold, that their hands are always cold. And then maybe one day you'll live with a man who has the exact opposite problem, and he'll always want to be turning the air conditioning on, and you'll be like, but I'm cold. And arguments will ensue. Because things and stuff, and smiles and tears, that's how life goes. But and numbers. Like thermostat numbers, which I think at some point, every household comes down to fighting about the thermostat. But chemical equilibrium is the same thing. The other thing you can think about it is, the best example of an equilibrium that I can think of is my treadmill. Right? My treadmill. I put it in front of my TV so I can feel like watching TV as a lazy idea. But I get on my treadmill, and what a pointless a thing the treadmill is. Our bodies must just, I just imagine going back in time to cavemen who had to like chase down animals, you know, and like just wear them out by sheer exhaustion by running distances and being like, hey, I run too. Yeah, I have this machine that makes it that when I run, I don't move anywhere. And be like, what is wrong with you?
I don't think they speak English.
And you can tell him that. Try talking to a
I don't
caveman.
think they speak science either.
Really? I think the cavemen had to be, they all
Chemical
had to be good
equilibrium.
scientists. We get to be lazy and let other people be like good scientists.
Oh, we had
they can feed us.
these.
So the treadmill is equilibrium because I provide motion forwards. Holy Lord, man,
And
would
the
you
shoes-
just stop?
If you are,
What is going on? I'm sorry. What the hell are you?
we can make it.
Oh, I live. That's pathetic. I literally just got like 5 different messages from 5 different people saying may the fourth be with you. I don't know why they all came in at once. I don't understand. But please love. But I don't know why they all came in one after the other. Anyway, so a treadmill is an equilibrium state because I provide forward momentum, but if I'm using it properly, the forward momentum I am providing is precisely equal to, yeah, and actually momentum isn't the term I'm looking for. I'm looking for velocity. But my forward velocity equals exactly the velocity in the opposite direction. And if that isn't true, the treadmill is going to give you some trouble, isn't it? Right? If it's going backwards faster than you go forwards, it's going to fling you off the back. Have you ever had that happen to them?
No.
Oh. On the other hand, I got distracted. On the other hand, if you went way faster than the treadmill, you'd go right off the front of this thing, which would also be pretty ridiculous, wouldn't it? So when you are on a treadmill, you are able to reach a perfect equilibrium state, where your forward velocity equals the backward velocity exactly. And from an outside perspective, it looks like stillness. Does that make sense? If you could run, but like do it with your hands like really, really, really still, and somebody just looked at you from like here, you would look like you're not moving at all, right? Even though there's tons of motion happening. And that's what an equilibrium is. To the outside observer on the macro scale, it looks like the reaction has stopped. Okay? But in actuality, at the chemical scale, the reaction hasn't stopped at all. The reactions are going, because they're always happening. It's just that the forward reaction is happening at the same rate as the reverse reaction. Some water naturally decomposes just by virtue of chemical reactions happening. Now, left to itself, without some outside source, that reaction is really slow, and it doesn't happen a lot. but it does happen. As it happens, the reverse reaction happens. Well, what? I don't understand.
It's made.
Literally, of course, with all of my technology today. So as some water decomposes, the hydrogen and oxygen that are present in the air around it is also combusted to make new water. And those reactions are constantly happening, but they're constantly in balance. And this whole unit is going to be all about learning how that balanced state works and about how we can adjust that balanced state to make chemical reactions go the way we want. So for example, when you did your aspirin lab, you didn't get 100% yield. In fact, most of you got around about 70%. And that's because two reactions are happening. One reaction which is making aspirin, and underneath it, the second reaction which is taking apart aspirin and turning it back into the stuff you started with. And a chemist's job, part of it, is to say a 70% yield is pretty wasteful. How can I change the equilibrium? How can I change the steady state? So instead of that equilibrium point existing where 70% of the stuff has become aspirin, but 30% that remains salicylic acid, how can I shift that so it's 90% or 95 or 99%? Because that's a lot less wasteful. And you may not think about that. Somebody says, here's a jug, use it. But like, if you run a gold mine, it's going to be important to you that you're not getting 70% of the gold out of the slurry you take out of the oil. Because you're literally losing millions of dollars in your waste oil. You're not going to do that, right? So a chemist's job is to use chemical equilibrium to change where that steady state is, so that, you know, when you run on the treadmill, you're in the place you want to be, right? Not way back. That kind of makes sense? Okay. Is there anything else I want to tell you today? I made a cheat sheet of this note for myself. Sorry?
Read this lab before.
Yes, but that's going to be for Monday.
I just noticed that.
So, so at equilibrium, the forward rate of a reaction equals the reverse rate of a reaction. On Monday, we're going to learn mathematically how to turn our rate laws into equilibrium equations. But not today. Today, you've got the remaining 25 minutes of class. If you have outstanding stuff, lab reports or whatever for this course, you can work on that. You can work on stuff for other courses. You know, maybe language-based ones if you feel so inclined. Are you guys reading in English right now? Okay, so listen, let me actually say that, like, Brave New World might be the most appropriate thing you could possibly be reading in the world right now. So I will cede to Mr. Lingell on this one that...
Nothing happens.
Oh, it's really good.
The entire book is about them getting rid of the only interesting people in the world.
Yeah, exactly. So have you guys, can I ask you, have you done like the other dystopians? Have you done like 1984 as well?
I've never done this.
I think we actually are supposed to do that, actually.
Because